Jack classified the Graph500 being about integer computation, the top 500 being about floating-point computation. And I have a little bit different take on that. I actually classified that Graph500 as being about data movement, memory interconnect, and the top 500 being about compute, both in integer and floating point. And so, with that little introduction to what we're trying to accomplish anyway, I'm going to turn it over to David to take with the information on the sixth list.
So is the microphone working?
Yes.
Okay. So the Graph500 really is now several years in the making under the leadership of Rich, Andrew Lumsdaine at Indiana University, and Mark Sneer of Argonne. How many of you have seen a Graph500 BoF before? Okay, so a fair number of repeats. We got started because there were classes of problems that we wanted to solve, but yet seemed to need a different architecture than the types of systems ranked on the top 500 systems. And so we needed a new benchmark to try to influence architectures to perform better in big data problems, and specifically we're looking at graph-theoretic problems. So this was an effort meant to complement, not replace, but complement top 500 for large-scale data analysis problems. And we formed a steering committee that's really representative of academia, labs, industry all around the world. And this is an open steering committee. And we've had some active debate about what are some of the right problems to include in the benchmark. So today, the Graph500 is ranked on a single kernel, the first kernel, which is doing breadth-first search, or a search problem, where a graph is explored concurrently, and that's used to rank the machines on the list. There are 3 kernels in total that we anticipate. The second kernel, there's been discussion and a draft specification for doing an optimization problem on a graph. And that's looking at single source shortest path, where you start at a vertex and you want to find the shortest path to every other vertex. So for those of you who are new to graphs, graphs are just one representation that are very useful for tying together disparate information. For instance, in a social network, vertices may be people, and if there are friends between them, you add edges between the representative vertices. These types of abstractions may be simple graphs, or they may have relationships on the edges. For instance, there may also be other attributes like timestamps, different types of edges, different types of vertices, and so on. So it's a very rich abstraction to look at big data problems with relationships.
David, I think the second kernel has a draft implementation too.
Okay, so there's a draft implementation, and the Graph500 website, graph500.org, has a lot more details. At the next Graph500 Birds of a Feather at Supercomputing in November of this year back in the US, we'll have more information. What we're asking the implementers to do is implement the second kernel, but still all the rankings for now will be based upon this first kernel. Now this is really a work in progress. As Rich mentioned, we announced this here at ISC back about 3 years ago at ISC 10. And we knew that this was a work in progress, and we've always said that we'll learn as we go. This is an entirely new domain, and we were growing in terms of folks who understood graph-theoretic problems, the types of systems that were going to implement this, and also the results. It's been a work in progress. So at the first Graph500 list that was announced November 2010, there are just 9 machines. And today's list that we're revealing for the first time here at the BoF, there's now 142 entries. So the business areas that we see in Graph500 span a number of domains, and these are just some representative problems, but not a complete list of the areas where graphs may be useful. So for instance, in cybersecurity and doing log analysis, looking at medical informatics or relationships between patient records, social networks like the example I gave a minute ago, data enrichment, and looking at the human brain or neuronal networks. These are all examples of problems that have different types of data sets, relationships between data, but the hallmark of these problems is that they're often very data-centric and typically not as much compute-centric. What you're trying to do is pull information together in ways where you often don't have locality to exploit inside the data set or the problem. It may be hard to partition these data sets. There may be ample concurrency, but the types of architectures today often have not performed well on these classes of large data problems. So Graph500 was introduced to try to push out that corner of the space to give us a way to compare machines and procure machines that could do better on these classes of problems. So graph500.org has a lot of information and historical information as well. You can visit it online, graph500.org, and there's where people can submit their results or look at the prior lists, as well as download some reference implementations. So let's get to the rankings, the moment you've all been waiting for. So statistics about the rankings first. As I mentioned, the number of entries are grown, and in the top, the Graph500 list, we're going to really cover just some of the top machines on the list, approximately the top 3 certificates and the top 10 results we'll cover now. The rest of the list you'll be able to find online. And following this and some brief comments by some of the more interesting results, I'll ask Torsten Hufler to come up and present the green Graph500, which is a complementary ranking looking at power efficiency in graph problems, which is a very important aspect as well. So that's the agenda for the BoF, and this shouldn't take the full hour, so you'll be out of here before you know it. So first, for Graph500, the entries that we have really represent international participation. This is broken down by country, and while you see that the US has a majority of the entries, it's still just about half the list. Japan has quite a number of interesting systems on the list, and you see the representation by a number of the countries represented here. And you'll hear more about China, which I think has some very interesting developments as well. So first, the top 3 systems will start at number 3, and if the representatives from the site, I'll invite them forward. So the way to read the certificate for Jugene, which is an IBM Blue Gene system in Jülich, the Graph500 measures a rate of performance on a graph in terms of edges traversed per second. So GE on the rate stands for billion edges traversed per second, and this is a machine with over 5,800 billion edges traversed per second. So taking a step back, the first list of Graph500, our machines had between 1 to 10 giga edges per second. This is 3 orders of magnitude more performance in about 3 years' time. So it's quite a substantial result. And the scale of the problem here, scale 38, is log base 2 of the problem size. So this means that there's 2 to the 38 vertices in the graph. 2 to the 38 represents 256 billion edges in the graph. That is an enormous graph. And the number of edges in the graph is several times larger than that. So over trillions of edges in the graph and a 250 billion vertices in the graph. So if there's someone from Jülich who is here? No, if not, we'll move to the next system in the top 3. The next system is at Argonne National Lab, and it's the Department of Energy NSC Mira supercomputer. This is an IBM Blue Gene Q, and the performance is over twice the number 3 entry, so 14,000 giga edges per second. And scale 40 is a graph that has 1 trillion vertices in it. This is, I believe, the first time on the list we've had a system with 1 trillion vertices and an order of magnitude more edges in the graph. So it's just quite an amazing result. Is there anyone representing Argonne here? Okay. Or IBM. We'll hand this off to IBM.
No, you just stay up here.
Stand up.
Okay, I stay up.
And the number one system is also an IBM Blue Gene Q. This is Lawrence Livermore National Laboratories, DOE NNSA Sequoia system, and it just by about 1,000 taps or giga edges per second beat out the mirror system. So this is Livermore's entry on a problem of the same scale, 1 trillion vertices. Quite an astonishing, absolutely phenomenal result. So I'd like to invite up Rana Stupinski and
Yeah, I was just standing.
and Kyung Bru from IBM. Congratulations. So I'll
make a copy.
You have, or just one?
I'll
I'll
give you.
send,
Yeah.
all right, send them a PDF.
So I'll now give you a little bit of a rundown of the list. And for those of you who are going to be in the top 10, I have your printed certificates up here. Any other submissions that aren't on the top 10, and even those that are, from the website you'll be able to download a PDF copy of your certificate and print as many copies as you'd like in color. So these are just the trends that we see. So this list, while we had more entries, the top entries stagnated just a little bit. And so this is representing in, let's see if this works. Here we go. The number one system is this middle line. The number 8 system is down here, and then the sum of those is this top curve. So what this is on the y-axis is log scale of the rate. So again, this is billion traversed edges per second, and then this is the list from the first to today's 6th list. And what we see is a steady progression of the top system, a little bit of a leveling out, so there's some improvement, but marginal. What this is saying is that we haven't really had that many changes in the top machines in terms of their performance, although there's some interesting tidbits that we'll get to. The number of cores used also has not changed that much between the last list and the current list. Again, this is the number of cores on a log scale, but quite impressive. We're at, over here, 10 to the 6 cores, which is we're on the order of millions of cores in these systems that are now running these large graph problems. And then the range from the number 8 system to the number 1 system is over in order of magnitude. So we expect by November's list, the 7th list, to see some interesting updates to these top systems. But this was more, not a lot of changes in those top entries. Now, looking at the vendors, just pulling out the 3 largest vendors, we see IBM, Cray, and then Convey with single node systems. So here's the top 10, and it's actually 11 because there's a tie for the 7th place. So in that first system, we saw, actually the first 3 systems were IBM Blue Genes, and after my presentation, I'll invite up IBM to say a few words about their implementations. The memory is quite substantial on these systems, 1,000 terabytes on that largest system. And you'll notice there's 3 systems on here, the 2 top IBM Blue Genes and the K computer in Japan that are solving a scale 40 problem. That is quite an immense problem. And then you see the gigataps, or billion traversed edges per second. These are phenomenal rates when you think about the first list just a few years ago, 3 years ago, only had about 1 in this column. Now we see thousands in this column.